So let's have a look at the results. I have processed this data to here now, and looking at the results, well, we have this correction of the terrain, which has been nicely done. And on the other hand, we can have a look at the spectra, which are quite nice looking. We have a strange peak here in the middle. This is mostly due to the interpolation afterwards, so up to here it should be nice, but in this interpolation range it tries to interpolate, and it creates an artificial spectrum which is not as nice as it could be. That's a matter of interpolation, and one shouldn't use these bands anyhow. What else do we see? Well, there's a little bit of O correction in the end. That's a known problem, that above about 2,450 the bands are not usable. One could even omit those because they don't add value there. There is a little bit of noise still in the data, so that's why I'd say one should maybe filter the data. One could filter maybe to a range of about 4 to 5 bands. I'd do some spectral polishing. So spectral polishing, some statistical filter, and this should reduce most of these effects. One should take, of course, the correct sensor. This was the high specs Mjolnir dual, that one. Okay, and what else do we have? The input file, maybe Savitsky-Golay would be okay, or we do a derivative filter. Maybe I'll do that one now, with 4 on each side, and smoothing factor of 2. This should result in some usable data. Let's call it just polish. I'll overwrite another output there, and then we just go through that one. This will take a second, so that's why let's wait. Let's have a look at the polished data now. So this is the polished one. Here it is, and well, we get spectra which are smoother than before. We may have some information loss in the shortwave infrared, so that's something to be analyzed if this was too much polishing. But spectra look more or less nice. There are still these gaps, so the interpolated gaps, which cause some strange features which are not really realistic. By the polishing, they may even have been extended a little bit. But that's something to be analyzed in the evaluation later. Having a look at the processed data, one can also check out the mosaicing, how it looks like. So I did some processing on this same data set for the mosaicing. So we have some mosaics here available from this data. So where are the mosaics here? Here they are. So first of all, the data before the processing, so how it looks like if you don't do an atmospheric correction. So you get this difference between the two data sets. So this is caused by the variable illumination angle. So the upper one has a very low illumination angle, zenith angle of 64 degrees against 48 degrees, which makes a 20% difference in brightness. This is caused just by the solar position. And if you have a look at this process data, that's the B21. This means IBRDF21, that's the model bit 21, which is a good compromise for incidence BRDF correction I'd recommend that one for this kind of data set. So we have a very nice correction for the on this side of the image. There is a little bit less correction on the right hand side, but it's still mostly corrected well. There are some problems, of course, regarding the cast shadows, because cast shadows cannot be corrected by this incidence BRDF correction, so the cast shadows will cause a difference between the two flight strips. Also, there is a difference on the very bright targets. That's something to be analyzed. So this may be caused by some BRDF effects which are not caught by this incidence BRDF correction, and one could try to do some more BRDF processing, but this would be more of experimental nature. There is some experimental method in development to improve this further, but so far this is not operational, and I tried some of that, and it's not leading to much better results than what we see here. So this would be the outcome of the whole processing, and this is where we are now. Okay, that's it.